Okay. So I'd like to welcome you all to the final Quantum Fluids and Isolation seminar for 2020. So today we have Dr. Edward Linscott. Dr. Linscott got his BS degree in physics and mathematics from the University of Cambridge in 2012. And he spent 1 year, and he spent the last semester in the University of California, Berkeley. And then spent 1 year at an honors program at University of Otago in New Zealand in 2013. And then he completed his PhD in 2019 from the University of Cambridge. And from November 2019 to present, he's been a postdoc in a group of Nicole Marzari at the Ecole polytechnique federale de Lausanne. So he's a recipient of the Douglas D. Crombie Award at Otago in 2013, the Cambridge Rutherford Memorial Scholarship in Cambridge in 2013, and the L.B. Wood Scholarship in 2014. And today he'll be talking about correcting the failings of DFT. So please help me in welcoming either by unmuting yourselves or by clapping virtually Dr. Edward Linscott.
Yeah, thank you very much, Joshua. So thanks everyone for having me. And so this is a picture of where I am currently at EPFL in Lausanne, Switzerland. And I personally find this particular picture quite entertaining, namely because of this building here, which is the Rolex Learning Center. And I can't think of anything more Swiss than a very fancy building sponsored by Rolex that looks like a thing of Swiss cheese. So that's there for my amusement more than anything else. But anyway, onto the physics. So today I'm going to be talking about a density functional theory, pointing out some of its failings, and then talking about the different methods that I've been working on, I've been using to try and address those failings. Now, I'm aware that some of you may not be familiar with density functional theory, let alone some of these various methods. And so I'll try and make this a little bit pedagogical and also address some more general concepts rather than really delving into especially specific results. So the general problem that we're all trying to solve really is this many-body electronic Hamiltonian. So where you've got some sort of system of electrons and nuclei. So with the electrons being the lowercase indices and nuclei being uppercase. And so obviously this gives rise to life as we know it, but a whole sorts of range of different and interesting physics. However, we can't really solve this Hamiltonian exactly, as we all know. And one of the main reasons, one of the main obstacles to this is the fact of the sheer dimensionality of the system. So the many-body wave function for n particles is 3n dimensional. And so the configuration space that you're dealing with just grows exponentially with the number of electrons. So if you wanted to try and do this with any sort of realistic number of electrons and nuclei, you couldn't. And in fact, in the Nobel lecture of Walter Kohn, he said, and this is, I think he was being deliberately provocative when he said that the many-body wave function for 100 atoms is, quote, not a legitimate scientific concept, which is a bit on the nose, but it sort of makes the point that actually practically it's of no use. And so we necessarily need to make some approximations. And so density functional theory is one such approximation, and it's quite a dramatic one. Basically, it's built upon these two separate steps. The first is the Hohenberg-Kohn theorems, and then there's the Kohn-Sham construction. So the Hohenberg-Kohn theorem states that there's we only need to think about the density of the electronic density rather than the many-body wave function. This is because there exists, so it's a statement of existence, there exists some energy functional, E of rho, such that for all densities, its energy, the resulting energy is greater than or equal to the energy of the ground state of your system. And also the energy of the this energy functional, if you put in the true ground state density, will give you the correct energy of that ground state. And so this is a statement of existence, but it gives you hope that you'll be able to construct something that practically means that you'll only ever have to deal with the density rather than the many-body wave function. This becomes practically a lot more useful with the Kohn-Sham construction. So what they did is they said, well, okay, so what do we know about this potential energy functional? So we know there's going to be a kinetic energy term. Here I've lumped in all of the nuclear terms, so I'm not going to think about nuclear motion or anything like that. They're just going to, all of those terms can just be absorbed into some sort of external potential. And we know that some sort of, that can be just written like this as a multiplicative potential. You can write down a Hartree potential, and then everything else that we don't know about it will lump into this thing here called the exchange correlation functional. So that contains exchange and correlation, like it says on the tin. The real breakthrough that Kohn and Sham made is that actually they pointed out that the ground state of this system here is exactly the same as the one that if you just replace all of these last terms here with this effective potential, that is simply the external potential, the Hartree potential, plus the functional derivative of this exchange correlation potential. And so if you replace all of this part here on the right with this sort of effective potential, the end result is you've got a non-interacting system, which must be solved consistently because now your potential is dependent on the density via this derivative here. And so what we've got is we've got the system of equations whereby if you've got a guess for the density, a guess for the electronic density, you substitute that in here and you generate some sort of effective potential. Then you solve this system of non-interacting electrons, and you'll get your these eigenstates, and you can plug those in and calculate the electronic density, and so on. And so you can loop through this into self-consistency. This is quite remarkable in that we've managed to reduce the many-body electronic problem to only look at the density, and furthermore, we only need to think about a system that's non-interacting. So that's much, much easier to solve. Of course, there's a catch, and that catch is that we don't know this exchange correlation functional, and so we must approximate it. And so there's a whole field of people who are involved in developing better and better exchange correlation functionals so that these results are more accurate. So this is all an approximate theory, but for all of its approximations, it works surprisingly well. So here's some very early results of the band structure of gallium arsenide with the experiment in the dots compared to the lines, which is the bands, the lines which are DFT calculation. This plot down here, these are some radial distribution functions of water so they're doing a molecular dynamics simulation with using density functional theory to calculate all the forces and to model all of the atomic interactions. So there's some quite old results and newer ones. Here's one here. This is a phase change material, so people will be modeling the processes of annealing and melting in these sorts of very large metals. Here's a calculation where they were investigating whether or not you can get biological molecules to form just out of very simple chemistry within in the absence of ribosomes, but on this iron and sulfur surface. And then some obligatory applications from, so this is from my PhD supervisor. They were looking at excitons within a protein and how they propagated and affected optics. And then from my current boss, here's a study where they screened a whole big database of 3D materials for potential candidates for 2D materials that would be easily exfoliable. And so these are all calculations done with density functional theory. So this is a lot of science that we're managing to do on the back of this theory. However, of course, it has its drawbacks. And so there are several failures of DFT which are well known. Perhaps the most notorious is the fact that the band gap is almost universally too small, and this is especially, the transition metal oxides are a really well-known example of this. So they are, DFT can predict some of these to be very small band gaps, or even conducting when largely they should be insulating with the band gap of several electron volts or more. And more generally, you've got these problems with the quote strongly correlated systems. So basically, we've got a sort of all of the mathematics behind density functional theory is the mapping to the auxiliary system, this auxiliary non-interacting system, is all well justified, but it does tend to work better when the physics of the real system does also happen to mirror those of our non-interacting system. So when you've got itinerant electrons that span throughout the entire subspace, throughout the entire system, and are very delocalized, and the interactions between them aren't especially strong and local. Of course, this breaks down when you've got systems like, say, the Hubbard model and the large U limit, where you've got localization. So you're not going to get that in density functional theory. And likewise, also when you've got these strongly correlated systems, even when they are teetering on the edge of this itinerant versus localization behavior, and you get some very interesting physics right at the border, and you're not going to get that with density functional theory. We also, the basic exchange correlation functionals will also not capture van der Waals interactions. This is because van der Waals interactions are a correlation of small electronic, electronic perturbations across very long distances, or comparatively long distances. And the basic exchange correlation function was only consider correlation based on the local environment and local density. And so they miss van der Waals interactions. This is less of a problem because you can add empirical corrections like the 1 over R6 minus 1 of the R12 sort of terms that we know from undergrad. So that's a more surmountable problem, but it's not immediate. It's not naturally captured by density functional theory. But then there are some more fundamental problems. So all of the maths I was talking about with the Holmberg-Kohn theorem, they only truly talk about the electronic density and the total energy. So here, with this plot of gallium arsenide's band structure, these curves are the eigenvalues of this auxiliary system. Formally, this has no relation to quasiparticle excitations. They happen to resemble them a lot, and people will use them as a proxy for quasiparticle excitations, but formally, those eigenvalues are meaningless, with the exception of the highest molecular orbital, which you can relate to some sort of density decay. But philosophically, you can draw the people draw a strong objection to that. And then secondly, we've also got issues with the self-interaction and static correlation error. Self-interaction error is one that I'm particularly interested in, and that's what a large part of the talk will focus on. So you've got one body self-interaction error. So the issue is that usually you've got some sort of Hartree term, which looks like this, where specifically we are not counting for the Hartree potential as experienced by some electron I. That's excluded explicitly from the sum of the terms of the wave functions that are contributing to the potential that electron experiences. Whereas when we turn over and just talk about the total electronic density in the Hartree term, that electron now experiences repulsion from its own electronic density. And so this leads to some weird behavior. For instance, in stretched hydrogen, so if you imagine, a stretched H2+ molecule, so if you imagine two hydrogen atoms that are very far apart, and there's one electron between the two of them, the ground state that density functional theory will give you will be half an electron on either hydrogen atom. Whereas really what we should have is we would have some sort of mix of having one electron on one atom and then one electron on the other atom. So, and this sort of can be more, this sort of idea is a bit more general. So here, if we think about just a general electronic system with some total number of electrons, and we're just thinking about how the total energy should change. So if we think in that example that I gave of the stretched H molecule, if we just focus on one of the hydrogen atoms, basically what you've got there is you've got a single hydrogen atom with half an electron on it, which is a sort of a bizarre item, object, but it's sort of meaningful in the scope of density functional theory. So if we now look here at this general system, when we have these sorts of systems with a fractional number of electrons, what we should have is we should have an energy that linearly interpolates between these integer number of electrons. So this doesn't happen. Oh, sorry, I've preempted myself. One of the consequences of this is that the energy of the highest molecular orbital for your system, which is given by the gradient just here to the left of the n here, should be equal in magnitude to the energy difference here. So this is the ionization potential, and because this distance between here is 1, then that means that the magnitude of that is equal to the magnitude of that. And this is an important property if these excitation energies here, which I said are formally meaningless, but if they can be related to these sorts of absolute energies, then they start to acquire meaning. So this sort of property is really, really desirable. However, if we look at Hartree-Fock, we don't have this piecewise linearity. Instead, you've got this concave behavior of the energy function of the energy. And so you've got this error. So you're going to have a highest molecular orbital that's not equal to the absolute energy difference. And so if we look at DFT, so what semi-local here is, so semi-local exchange correlation functionals are sort of the standard entry-level exchange correlation functionals, and they tend to exhibit concave behavior, concave convex. Either way, I'm from New Zealand. I get these things upside down. I'm allowed. Yeah, so here you can see that we're going to, again, those molecular energies are not going to agree with absolute energies. And so there are all sorts of consequences here for you. This is one of the reasons, this is the reason why you're going to, the DFT gets a small band gap and it gets the wrong ionization potential, which is what I was just looking at. So the ionization potential is exactly the energy when you remove an electron. So this energy difference here, and electron affinities, which is the energy difference when you add an electron. So to deal with these various problems with density functional theory, I'm going to talk about 3 different methods: DFT+U, Koopmans spectral functionals, and dynamical mean field theory. So just launching straight into the method 1, which is DFT+U. So DFT+U is inspired by the Hubbard model. So we know that DFT does transition metal oxides poorly, but we know that the Hubbard model has successfully explained the Mott insulator. And so the motivation was, well, perhaps if we manage to integrate the Hubbard model into a DFT framework, then perhaps the resulting theory will inherit the Hubbard model's ability to accurately model transition metal oxides. So I start off with some sort of electron interaction term for the derivation. You make various assumptions, which I won't go into detail, but the end result is you finish with this corrective term to density functional theory. So we've still got now some sort of DFT+U density functional, and all it is, it's a correction to, so you've still got the density functional theory functional, but then you just got this additional term here, which is this, this part here. And so this correction is selectively applied to spaces where which are suspected to be correlated. If we look at this correction in detail, so here's an example. So here's a transition metal. I think this is manganese, sitting surrounded by 6 water molecules. And so we know that the 3D subspace of these transition metals is correlation is plays a large factor in the electronic structure, especially in the 3D orbitals. And so what we want to do is we want to selectively apply the DFT+U correction to the subspace spanned by these orbitals. This matrix here, N, so I is the atomic index and sigma is the spin index. So this here would be a so a 5 by 5 matrix, just one for each one of these orbitals. And so it's just the projection of your density matrix down onto the subspace bound by these 5 orbitals. And then what actually this corrective term does is a lot more transparent if we actually look at the resulting potential. So if we imagine that we've got some sort of electronic state that's got a very significant overlap with that subspace, and that state is filled, then this Nij will be equal to 1. And so this whole term here will reduce down to a rigid shift of minus U over 2. So U here is a scalar parameter that determines the strength of the corrective term. So filled states are lowered by U over 2. And if Ni of j, if we're looking at an empty state, then this Ni of j is 0. And so that they will be raised by a factor of U over 2. So ignoring relaxation effects, what this corrective term is going to do, it creates a gap of size U between filled and empty states with appreciable overlap on this particular subspace spanned by the orbitals. So the previous explanation that I gave in terms of its historical derivation as derived from the Hubbard model has fallen a little bit out of favor, namely because a few of the steps in the derivation are quite hard to justify and are a bit arbitrary. And actually, there is quite a compelling link between DFT+U and this anomalous curvature that I was talking about earlier. So if we consider this DFT+U correction term, but now think about it in a basis of orbitals that diagonalize this matrix, then this is what we've got here. And so this is a term that vanishes where the occupants, wherever these values are 0 and 1. And so if I plot this on this axis here, you get this red curve. And so we can see that if I'm going to add this red curve to the green curve, I'm going to get something that's close to being piecewise linear, which is what we desire. Of course, this depends on me getting the right size of this U parameter here, because that's just going to scale the total height of these bumps, which actually is incredibly helpful because I can actually explicitly measure the curvature of these lines here with a density functional theory calculation. And so I can do a DFT calculation, measure the curvature in that's present, and then choose a U value that will precisely cancel it. And so this method by Koopmans basically makes DFT+U what you could call a self-correcting DFT. So it's a density functional. The density functional theory sort of reveals the errors within itself, and you can then correct those. So it's quite a nice theory. So just to present some results, here are some calculations that I did on manganese oxide. well, specifically the ones I did are these ones down here. So these are some DFT calculations compared to experiments. So I've just focus on these ones down here. So this is the indirect band gap. And so PBE is one of these entry-level DFT functionals. And so it gets a much smaller band gap than experiment. Whereas if we add a plus U term, and these are various flavors of DFT+U, then you get a band gap that is much more accurate. Likewise, with the magnetic moment, again, PBE underestimates the band gap. And once you add the plus U corrective terms, you get a magnetic moment that is much more accurate. Now, there are some caveats to this. So we know with, so here's this plot here, finally, is looking at the valence band edge character. And so we know for the transition metal oxides that the early transition metal oxides, so your titanium and vanadium, they are Mott insulators. So the band gap sits between you've got your lower and your upper Hubbard bands. And the later transition metal oxides, they're in the charge transfer insulators regime. So you've got a gap between your transition metal, the oxygen 2p bands and the upper Hubbard bands. And manganese sits in the middle of these, so we should expect some sort of valence band character that is a healthy mix of both manganese and oxygen character. Oh, sorry. And what we find is that we already get a good mix with PBE, but if we apply a DFT+U calculation, and I'm just focusing on these white lines here, this is what we get if we apply a plus U correction to the manganese sites only. And so what's happening here is that if you can imagine, so we've got our manganese and our oxygen orbitals, and if we apply a plus U correction to our filled manganese orbitals, so these are currently bonding with one another. If we apply DFT+U correction, these manganese orbitals are shifted downwards in energy, and so that destroys the bonds with the possibility of hybridization between the manganese and oxygen bands. So what you can do to correct this is you can apply a plus U correction to the oxygen 2p subspace as well. Now, of course, the oxygen 2p electrons you wouldn't say are conventionally strongly correlated, but you can still do the same procedure and measure the curvature that's present due to in those oxygen 2p subspaces. And if you do this, you get these values that are back up here, closer to what we'd expect. Now this issue presents itself a lot more clearly in molecules. So here's a very similar system. So again, this is that hexahydrated transition metal. And so what happens here is if we apply a plus U correction, so this is what I'm doing here, I'm increasing the value of U, and I'm keeping an eye on the axial bond length, so the distance between this atom here and this water molecule here, and this is the range that it should be experimentally. And so we start off just outside, but more or less within that range. But if we keep on increasing U but only on the manganese atom, it destroys that bond, and as a result, the oxygen atoms drift apart. And this is unphysical. Thankfully, if we apply a correction to the oxygen 2p subspace, we get back to this nice alignment. Here, DFT gets the geometries pretty good for these systems. So to see those on the straight line is satisfying. So just to summarize our DFT+U, there's strengths are that it's self-correcting, which is incredibly nice. We don't need to know anything about the system. We don't need any sort of experimental data to decide on a U parameter. We can choose the U parameter to precisely cancel the curvature that's present in the system. And also it's computationally inexpensive. All that we're doing here is we're adding an additional term onto our energy functional. So in terms of the scaling of these calculations, it's a negligible cost to go from DFT to DFT+U. with the exception of the fact that you now also have to do calculations to calculate the U parameters. However, there are a number of drawbacks with DFT+U. Some of these I've touched on already. The first is to do with the nature of where and to what orbitals you apply the +U correction. So before I was saying, well, we could apply them to the manganese 3D subspace, and then we applied them to the oxygen 2p subspace. And the question is, where do you stop? It's somewhat arbitrary. And so in terms of the number of subspaces that you apply it to, and also those orbitals, you can define them in a number of different ways. So you can use some sort of atomic orbitals, you can use Vanier functions. So there's an arbitrariness in that as well. There are complications due to the added idea of self-consistency. So what I mean by this is that if we're going to do a DFT calculation to then calculate what the curvature is, and then generate a value for U, then what you can do from there is you can then recalculate the curvature and then tweak your U value and keep on doing that until you eventually self-consistently calculate U, which probably is wrong of me to put in the weaknesses column. It's just an added complication, really. But now there are some more fundamental issues with the DFT+U method. The first is that it's always going to increase the band gap. So as we saw, basically it's going to amount to a rigid shift between the filled and unfilled orbitals that have got significant overlap with your subspaces. And so it's lucky for us that we've got DFT tends to underestimate the band gap. And so this is going to increase the band gap. So it's probably going to head us in the right direction. But we don't know for the right reasons. So it's sort of a bit unfair of me to list all of these different methods like this and say that we're doing better, because we're not really sure if we're doing better for the right reasons. After all, one of the approximations that you have to make in the derivation of DFT+U is you have to assume you've got a single Slater determinant. So actually, all of the physics that we've got here is nothing more than a mix of, so we're mixing in some Hartree-Fock into the equation. So you're not going to get any truly many-body effects. And finally, in the tradition of every physics lecture, I told a white lie earlier in that I failed to make a distinction between local and global curvature. So what I mean by this is the plot that I showed you, and I told you that the red curve, you can add it to the green curve, and we'll get back to you'll get back to something that is piecewise linear. However, that's not entirely true, and it's a bit misleading of me to plot this red curve on this diagram, because actually this is not the total number of electrons in the system. Actually, what this is doing is this is actually correcting curvature that is present locally in that subspace with respect to the occupancy of those local orbitals rather than the total number of electrons. So that's what we call local curvature, whereas really the issue is with this top graph here is the issue of global curvature. Now, if people have demonstrated that if you correct local curvature, then you can go some way to correcting global curvature, but they're not the one and the same thing. And so that's just an important distinction to make when thinking about DFT+U. And so that nicely leads in to the second method I'm going to cover, which is Koopmans spectral functionals. Sorry.
Excuse me,
yes.
my question or commentary. It's a bit unhumble, but I cannot resist it. You realize that the inventor of LDA+U has been listening to your talk right now.
Sorry?
I'm Mr. Zanen of Anderson. What is
yes.
Zanen Anderson, right? And I really designed it. I mean, a lot of credits go to my colleagues, especially Vladimir Nisimov, because he put on the map eventually. You gave a very nice overview, and I really like this last bit, right, which is not consistency. That's really a significant progress. But I'm just wondering about it. We were all along aware of the shortcoming, right, of this orbital dependence, etc. But the way I always like to understand it is that it's sort of a much deeper problem. So the whole notion that Hubbard models exist is in essence empirical, right? So you can argue from the atomic limit, right? That there are you. At the moment that you form a solid, you don't quite know what you're doing. Nobody's ever done a controlled computation out there. And then sort of like in the era before I invented LDA+U, I was busy with doing photo emission, interpreting photo emission, right? And the early photo emission was telling back then that there are these Hubbard band, blah, blah. Right, so we knew that there was reality to the Hubbard model, right? That's the real reason to say we should worry about it. Now, the trouble is, of course, that normal LDA departs from an extension that departs from the homogeneous electron gas, and it's all long-range Coulomb interaction, right? While the +U departs from the atomic limit, right? And you get an intermediate coupling regime. And why should there only be local use to worry about? You know, there should be remnants of long-range Coulomb interactions and three-side exchange, mates elements, blah, blah, blah. Right, so isn't that the real problem, that, you know, you don't really know how to approximate your interaction potential? I mean, because you hang in between the free electron gas or homogeneous electron gas and atomic limit.
Yeah, I agree absolutely. I'm not sure what more there is to say.
Yeah, that is, you know, just
no, agreed. And I probably shouldn't think of say that these are weaknesses, more as sort of limitations and things to keep in mind. Like, it's a great method and I use it.
It's always like, it's great for lantern knives, you know, these four orbits are basically +U-ish. When you have sort of large band gap multi-insulators nickel oxide, it's quite good. You go to vanadium oxide, V2O0 such, right, and you know about all the trouble. It's just failing. I mean, it's estimating when you use your honest U, you know what you would calculate with your self-consistent method. I think you have in your hands.
Yeah, it's great. Thank you. Okay, so now I'm going to talk about the second method, which is Koopmans spectral functionals. So the Koopmans spectral functionals take a slightly different approach, but they're actually they've got a lot of parallels with DFT+U. So again, we're trying to face this problem of this erroneous curvature. And what the Koopmans compliant functionals do is that we assert this condition. So we want to assert that our eigenvalues are independent. So these are our eigenvalues of our Kohn-Sham eigenstates. These should be independent of, so this f of I is the occupancy of that orbital. So if you can imagine that I've got some orbital and I'm slowly filling it, I don't want the energy of that orbital to change. Because you can imagine that if I had an orbital and I just changed its occupancy slightly and then its own energy changed, you could say, well, it looks like that energy is interacting with itself. There's some sort of self-interaction. So, and it's actually quite straightforward to construct a correction mathematically that actually explicitly imposes this condition. So these are, well, you might catch me calling them, so KC is Koopmans compliant functionals or Koopmans spectral functionals. So this is the correction. It's in the similar sort of spirit to DFT+U. So what you've got an energy functional. That's the underlying DFT energy functional plus a corrective term. And so if we imagine, say, we've got this system here with n plus some fraction of electron, another fraction of an electron. So this is the DFT energy that I would get. What this first term here does is it traces me back along this curve from f of I back to the empty orbital. And then we fill it here with this term that's linear in the occupancy of that orbital. And so that's heading in the direction of this n+1 data point here. And so what you can see is that this term just immediately inserts in the linearity of the number of electrons, of the total energy with respect to the number of electrons, as we progressively fill one orbital after the next. Now, there are some important ways in which this differs from a standard density functional theory. The first is that we've got this we've got an orbital density dependence. So now our theory is no longer what you could say is a density functional theory. We've now got a dependence on the occupancy of particular orbitals. So it's an orbital density theory, which makes things slightly more complicated. And then we've also got this screening to take account of. So when I was making these arguments here before, I never entertained for the possibility that as I'm emptying and filling this orbital, all of the rest of the system will screen this. And so you can take account of this by prepending this correction with this linear alpha term. So this is just going to have an alpha term for each orbital. And what this does is that it takes into account for the orbital relaxation. You can kind of think of it as an approximation to the dielectric function. And you can calculate it using much like DFT+U, you can calculate the right value of alpha to use via a series of DFT calculations that will give you the linearity factoring in the orbital relaxation. And so this is quite nice because now, as opposed to with DFT+U, when you're applying it selectively to some sort of subspace, we're now applying this to every single orbital in the system. Is there anything more I want to say about that? I don't think so. So here are some results. So here, these are looking at the electron affinities and ionization potentials of this set of 100 different molecules. So these are anything from benzene rings to there's waters in there, carbon dioxide, some metal dimers, some DNA base molecules. And so here's a result looking at the ionization potential and comparing the ionization potential that you get against high quality quantum chemistry results. And so in red here, we've got these are three different flavors of Koopmans functionals. And so they're right up the top in terms of methods that are giving the smallest mean absolute and mean signed errors in the ionization potentials. And here's some work of mine that we've been doing recently looking at the electron affinities. So this is now the process of adding an electron to the system. And this is now comparing against experiments. So we've got Ki, which is our Koopmans spectral functional, and it gives a mean absolute error competitive with delta CCSDT, which is a high quality quantum chemistry result and a much, much, much more computationally expensive calculation. And our mean signed error is great as well. And so here you can see in comparison, PBE just systematically will get your electron affinities wrong. So this is really, really encouraging. So just to sum up with these Koopmans spectral functionals, the strengths are now that we're there systematic, so we now apply these to the every single orbital in our system. I've got under the strengths and the weaknesses the fact that it's an orbital dependent theory. So yes, it complicates things from a practical standpoint, but actually having an orbital dependent theory is a natural generalization of a density functional theory. So that basically you can think of the exchange correlation functional density functional theory as the best possible approximation to the exchange and correlations self-energy, which really is a dynamic and non-local quantity. Now, you can show that if we want to just capture the spectral potential, so now, the spectral density, so now we're not just interested in capturing the ground state density, but we also want to capture exactly the frequency component of that as well. Then you can adopt a local and dynamical potential instead of the exchange correlation potential. So now we've got dynamics in the potential. And if you then discretize in terms of the energy, then what you're left with is an orbital dependent density, dependent theory. And so basically you can sort of see it as the next step along. So what we're doing is an orbital dependent theory is one that takes into account for some of the dynamics of the self-energy. And so that's sort of why we start to approach sorry, I was comparing here, I didn't explain. This is generally compared to GW calculations, it's a perturbative method, which is analogous to screened Hartree-Fock. But so, yeah, so orbital dependent makes our life more difficult, but it's kind of a natural generalization. The results are hard to argue with, they look great. However, we're somewhat limited in our scope at the moment. So firstly, we've only managed to formulate the Koopmans spectral functionals for insulators. We don't quite know what to do when there's no just real gap between the conduction and the valence manifolds. And also it's untested on strongly correlated systems. So it's all very well to ensure the linearity, but that's only one of many errors or many potential errors in DFT. And so while we have corrected the linearity, we're actually yet to see, how far this gets you when it comes to these strongly correlated systems. So in the last couple of minutes, I will just very briefly talk about dynamical mean field theory and some of the calculations that I've done with that. So dynamical mean field theory, so we are interested in these sorts of biological systems. So what we've got is so just say to focus on this one, so this is myoglobin from the blood, which is here you've got this iron atom that binds, well, hopefully to molecular oxygen. In this instance, it's a binding to carbon monoxide, which is less great. But here we've got a correlated subspace where we're going to have strong correlation that's very distinct. So I'm going to return to the language of DFT+U in terms of we're going to have this subspace where strong correlation is important, and we want to selectively deal with that, that subspace. So the way that we do this is if we just focus here on this flow diagram here on the right for a second. So we start off with some Hamiltonian for our system is calculated with density functional theory. And what we want to do is we could trust DFT to do the calculation for all of the ambient protein, but we want to apply density dynamical mean field theory, sorry, to deal with the correlated transition metal 3D subspace. And so what we'll do is we'll project these various quantities, so the Hamiltonian and the self-energy, which we'll guess to be 0 to start off with, and you can calculate the Green's function. You should project these down onto your correlated subspace, and then what we do is we map these onto an Anderson impurity model. So this is a Hamiltonian here up here for our Anderson impurity model. So you've got, and here's just a diagram of what's going on. So you might have a Hamiltonian, which has got, say, 11 sites, and 5 of these will correspond to the 3D orbitals of your transition metal 3D orbitals. And then 6 or 7 that you play around with the exact number, but these just stand in for the rest of the ambient system. So in my case, it would be the rest of the protein. And basically what we do in the process of this mapping is we choose these hopping parameters, epsilon and v, such that the physics of the ambient system is most accurately captured by these bath sites, or specifically the Green's function of this Anderson impurity model. We try and make sure that that's reproduced as accurately as possible. But the end result is, having done this mapping, you now have this Hamiltonian, and the important distinction now is we've got this interaction term here, H of U, which has now got some honest to goodness many-body physics contained within it. And so now we've got the possibility of getting things like satellites and quasiparticle lifetimes, etc., coming out from this theory, as opposed to previously where none of that was actually possible. So previously, by which I mean the Koopmans spectral functionals and the DFT+U. And so we then, having constructed this Hamiltonian, we then solve it and acquire the self-energy, and then that's upfolded, so you map that back onto the actual physical system. And so what you do is you can then iterate these and end up with basically this solving for the self-energy where you've and yeah, so you solve this to self-consistency, and then once you're done, you've got the self-energy and the Green's function of your entire system. So very quickly, here's just some results on this crabs. So this is crabs blood. So this is the analog of myoglobin, but in crabs, instead of using iron to bind molecular oxygen, they use these 2 copper atoms. And so I should have noted that this interaction Hamiltonian, once more, we've got this U term cropping up. So this is basically, you can think of U as, now I'll just treat it as like a scaling parameter for how important I'll play around with how exactly large that U is to play around with how much the many-body physics I include. And we know for this particular system that it exists in a D18 singlet. And so we've managed to show that actually to get an appreciable fraction of the this subspace B in this D18 singlet is you actually need to drive U to about 7 or 8. So this is basically another way of saying that actually in this system, to get the experimentally observed results, many body physics is important. I should probably wrap up. So dynamical mean field theory, its strength is obviously it's accurate. You've got truly many bodies, so you can get these sort of real many body effects. The weaknesses, well, the relative weaknesses. So there's still, of course, now we're back to the same problem of having this arbitrariness to do with the correlated subspace. There's less of an issue to do with how before I was saying that you also might want to apply the U correction to the oxygen subspace, because the nature of this mapping of these parameters to these epsilon and V parameters means that you don't destroy bonds that exist between the impurity sites and the rest of the system. However, of course, this is a much more expensive method compared to the previous 2 that I've presented, and getting it to converge can be a downright pain. But yeah, it's you can get some. It definitely has its use cases. Yeah, so with that, I'd like to conclude. So yeah, so you've got DFT+U, it's self-correcting. We've got some arbitrariness to do with the different subspaces that you apply it to. Koopmans spectral functionals, they're systematic, but at the moment we've only formulated them for insulators. And dynamical mean field theory can be difficult and expensive calculations, but you start to introduce true many-body physics into these really interesting physical systems of really interesting realistic size for applications. So with that, I'd like to acknowledge all of the various people who helped me with this research, and thank you very much for your attention, and invite your questions.
Okay, so if you have any questions, you can either just unmute yourself or you could raise your hand virtually. So maybe I'll wait well, I actually had one question. So what would you say is the next step, basically, in this research? So what are you doing now? How do you plan to extend this even further? Like, what are open questions, basically?
Yeah. So currently my work is focused on the Koopmans spectral functionals. Mm-hmm. I mean, obviously the insulator issue is a big issue, mm-hmm. and we'd really like to resolve that. And then there's also interest in exactly including dynamics really explicitly. We'd really like to be more systematic about it, because basically at the moment we sort of take this ansatz of the energy of the orbitals being independent of the occupancy of those orbitals and just construct a functional. We would really like to actually be able to start from some sort of perturbative expansion and gradually actually derive and make several approximations and arrive at the Koopmans compliant functionals, so that at that stage it sort of becomes a lot more natural to know actually how to expand it naturally mm-hmm. in a really rigorous way. And so that's what we're quite interested in at the moment is trying to work out systematic expansions to it. But also on the other side of the coin, we're actually spending a lot of time working on how we can actually simplify it further so the calculations are faster for practical use cases, because so actually to calculate those alpha parameters for every single orbital is a bit of a pain. And so a large part of the work that I've been doing this year has been automating that process. So yeah, so there's lots of interest both in terms of the theoretical side, trying to push the theory, but also just in the practical side in terms of making it a practical theory that's useful for people doing science.
Okay. Any other questions for Dr. Linscott? So maybe I'll wait 5 seconds. Okay. Oh, yes.
Sorry, could I ask a question there, Dr. Linscott? It's about going back. Thank you very much for your talk. Sorry, just to start off. It's going back to your global curvature. Would you be able to go back to that slide? Thank you. So when I saw that you have the total energy difference between the n electron system and the n-1 electron system is the Kohn-Sham eigenvalue of the highest occupied orbital. Am I saying it right, or?
Yeah, hang on a second. So, well, I suppose this is a good one where it's not really, but yes. So if we have this linearity, then we've got this, Kohn-Sham eigenvalue should be equal to this absolute difference.
Yes, and then if this condition was satisfied, and then you want to look at the energy difference for the n-1 system to the n-2 system, would that be the Kohn-Sham, highest occupied Kohn-Sham eigenvalue for the n-1 system, or is that the Kohn-Sham eigenvalue for the second highest occupied?
No, it would be the former. So I mean the exact number of the n that I've chosen here is arbitrary, right? So you could just draw exactly the same plot but centered on the n-1 point. And so the interesting point here is that actually these things really should definitely be exactly the same, because we actually know that the decay of the density of the electronic density in the far away from nuclei should be given exactly, can be related exactly to this HOMO energy. And so it's something that DFT should actually get exactly right, because that's related to, that's an electronic density property. It's not even an excited state property. So this should really be a criterion that DFT should fulfill. But DFT has got issues with in terms of the decay in the long regions. But sorry, just to come back to your question, just answer it explicitly. Yes, so it would be this. You can imagine if I did a calculation of a system and I just removed an electron, and then I could you could work out the energy of the n-2 electron system in two ways. One is you could explicitly calculate what it was by just removing 2 of the electrons and doing a DFT calculation. The other is removing 1 electron and then doing a DFT calculation and looking at the HOMO. Now, I guess that begs the question, well, why don't you just do a whole lot of sort of just calculations at different numbers of electrons? And really the interest is that we'd like to just do a single calculation, and this should contain all of the sorts of excitation properties inherent inside of it already. So we want these sorts of we want these energies that we're using as a proxy for quasiparticles to fall out immediately, rather than having to do all of these different finite difference calculations.
Okay, no, thank you very much. That makes a lot of sense. Yes, but could I ask is there any, using that method, then there wouldn't be the DFT+U method, there wouldn't be any way to assign meaning to the other Kohn-Sham eigenvalues then, would it? Because it's telling you about, it's giving you more information about the n electron system, but it wouldn't it wouldn't fully solve that issue.
So there is more information in that. Basically, so if you imagine, so the say the energy of the HOMO -1 would correspond to an excitation whereby you pull out an electron from the second most. There's you know, that when you remove an electron from that orbital, while keeping electrons in the nth orbital and the n-1th orbital. So you can imagine basically what we're doing is we're creating a hole below the, you know, we're not just pulling an electron that's the outermost one, but we're pulling one out that's slightly deeper. And so of course that's just nothing more than just, you know, you're looking then at sort of spectral properties, right? So all of these different eigenvalues should have meaning. They'll correspond to sort of basically you can imagine some sort of photoemission or photoabsorption, whereby you're removing one particular electron that's not necessarily the outermost one.
Oh no, okay, thank you very much. You know, that makes a lot of sense. Thank you. And thank you for your talk as well.
No problem.
Okay, any other final questions? Okay, let's maybe thank Dr. Linscott again.